Good morning. I'm very happy to be here today. Very happy that you are here. I was hoping it would be you. I've been wandering around thinking, I hope it's them. And here you are. So I'm Eliot Crowe. I am a program manager with Lawrence Berkeley National Lab. We're based in California. We do a lot of research funded by the federal government. And I'm here today to talk about some research that's just wrapping up right now. We were looking at data from fault detection diagnostics tools, going through many millions of rows of data so you don't have to. And I think it's, there's a lot of talk about analytics. I see it a lot here in the commissioning field. And I think sometimes for those people who are looking to take on these kind of tools, it helps to understand what you're going to actually get once you get those tools working for you, what you really have to deal with. And just for a quick show of hands, who is currently using an FDD tool actively in their work? Okay, that's great. Who has used it or they're planning to use it? Okay. And raise your hands if you haven't raised your hand for any other question yet. Okay. It's important you all feel involved here. So what I'm going to talk about here is the outcomes. We have kind of three main pieces to the research questions I'm going to talk about here today. One is, what's the volume of faults that you may find being thrown at you if you use these tools? Another is about what are the most common faults? So what are the things that are going to show up most often? And the third dimension brings in a time factor there, which is for those faults that do occur, are they happening every day, half the days, occasionally? We have some data on that as well. And for kind of a sneak peek at what the conclusions really point to here in really broad terms, you're a commissioning crowd, so I'm going to throw you some red meat here because I think that the need for people with your skills is really emphasized by this work. And I think also the need for these kind of analytics tools is really emphasized here. There's so much in modern buildings that could go wrong that you need to stay on top of, and also for what goes wrong, you need to be able to diagnose it, which is where your skills come in. I'll go very briefly through the boilerplate slides here. Read that quickly. Okay. So I'm going to start, for those that are less familiar with these tools, I'll try not to spend too much time on this, but I want to just make sure we're on the same page on what these tools are. We love acronyms, of course, so we kind of promote this umbrella term, energy management and information systems, which is just a generic term for those tools that pull in all this data from building systems, from building automation systems, lighting control systems, weather forecast data, meter data, etc. Pull that into some kind of unified database, normally in the cloud, and then you can overlay these capabilities. Looking at monthly data analytics is a best practice. You cannot get so much granular data from that, but if you have smart meters, you can go that one level deeper. Look at an energy information system, or EIS, which is where you can look for energy consumption anomalies during unoccupied hours. You can also do M&V on all the improvements that you implement through your programs. Then you get to fault detection diagnostics, which is the main topic of this presentation today. I think that if you hear the definition of FDD tools, I think it's very easy to kind of clue into this idea that they're going to spit out a list of faults, things that are wrong. You need to go do something about this, and that is what they do, and they do it well. They might do it with machine learning. They may have some logic rule-based algorithms, but you're going to get that list typically. But the piece that's emphasized less is the fact that once you have this list, you may need to do a bit of extra diagnostics. Sometimes, for example, it might say, hey, your mixed air temperature is out of whack. You may have to some other data points that mix in there, but you may not actually know what the root cause is. The analytics can't always do that. And so what fault detection diagnostics tools also have is the visualization tools and the analytics to actually drill down deeper on these alerts to actually find out what the root cause is, and that's where people like you come in, who can actually understand the underlying systemic issues and look to where the actual fault is occurring in its root cause. The bottom category here, ASO, Automated System Optimization, it kind of takes that one step further in a sense where if you want to feed in your utility tariff information and make sure that you minimize your peak demand cost charges, or maybe you just have peak demand targets you want to meet. ASO tools vary the system dynamically, continuously, automatically to minimize certain things, whether that's cost or peak demand. They're less common, and typically they're more narrowly focused. Maybe they're on the chiller and pumps, or maybe they're on the air side, whereas FDD really can feed whatever data into that that you want. And this sort of presents it as if they're discrete tools, but there's no reason why you can't have a tool that does all four of these, two out of the four. So you can do a lot of things with these capabilities. Today, I'm going to talk about the FDD side, as I mentioned. I'm going to briefly touch on the costs and benefits side, just because we researched it for 5 years, and by God, we're going to tell everyone about it. Over the years, there have been many studies. The results I'll present here from a study that wrapped up in 2020, and we had about 500 million square feet of commercial space that had implemented these kinds of tools or were in process, and we got their actual consumption data and information on what they were actually doing in response to their analytics. And what we found was that for the energy information systems, that those, I'm not going to cover everything in this table, just focusing on the right-hand column here, and the presentation is there for future use for anyone who wants it. So 3% savings at the whole building level for energy information systems. So this is using the smart meter data to get more intelligent about how you manage energy use, track it, and maintain your savings. For fault detection diagnostics, we saw data showing 9% median energy savings at the whole building level. And for anyone who's done commissioning, that's kind of in the ballpark of what you might expect. And you know that some buildings you're going to get more and some buildings less, but that really is lining up pretty well with that. What's an interesting coincidence is that for energy information systems and the fault detection diagnostics, different levels of savings, but you find that FDD is more expensive, and they pan out to be about the same payback, less than 2 years. So in each case, pretty good payback. And again, that's not dependent just on the analytics. You have to actually have a process for using them. For the ASO, you can find technical papers and case studies that may have some pretty significant numbers, but there's not really enough data to come up with some generalized rules of thumb about that. They've been around for probably over a decade, but they're still not massively being adopted in terms of what we can see publicly at least. And for anyone who's interested, we did publish a report on this about 18 months ago, and this will have more detail on the numbers I just presented, and also it goes into other dimensions of management. So what are the most common improvements that are implemented in response to having these analytics, and also the ways that owners are perhaps managing these things in-house or using a third-party commissioning provider to support this work, and some of the sort of enablers for success you'll find in this report. And this is free to download for CX Energy attendees and anyone else in the world. All right, so that was kind of the preamble to talking about the research that I'm here to mainly present here today. So in 2019, we kicked off this study. It's funded by the US Department of Energy. We're supported by the Pacific Northwest National Laboratory and also University of Nebraska-Lincoln. I was talking to some Nebraskans earlier this week, and I think I may have to say something like "Go Huskers" at this point, and maybe something about Iowa, but I'm not going to go there. So this research was really into looking at what really happens when you implement the fault detection diagnostics tools. What can you really expect to see? And some of the angles, as I mentioned in the introduction, are which are the HVAC faults that are most often observed to be present, And we had to kind of pick our words really carefully here, because what you see reported by an FDD tool isn't always the truth. There can be, depending on how you set your trigger thresholds, things get reported or not. Or maybe there's some false alarms due to data communication issues. There are some uncertainties. But I think what I really want to keep coming back to is the fact that if you are a user of FDD, your experience is based on what it's going to tell you. And you're going to have to work out what those uncertainties are. You're going to have to prioritize what it reports to you. Hopefully this gives a sense of scale of what that looks like. The other piece of this is really about that volume. We hear often anecdotally about how these analytics tools can really result in some data overload. That's a real thing. We've kind of put some numbers to that right now. And again, it's something that, you can't be scared of it. You just have to find your way to manage that. And I'll have questions for you on this also. So if you came here to check emails and take a nap, I may call you out. So, FDD tools can be connected to whatever data you've got. Can be connected to the meters, chillers, pumps, air handlers, rooftop units, terminal units, etc. We could not eat that whole elephant at once. So our focus in this study was on the air handler side, the terminal units connected to those air handlers, and also on rooftop units. And through the study, we actually connected with 6 FDD tool developers who were very gracious in giving us lots of data, and also one large building owner that's a user of FDD shared their data with us as well. And what we ended up with was over 3,500 air handlers worth of data, almost 55,000 terminal units that were connected to those air handlers, and then almost 8,000 rooftop units. And this was data that we were given that in almost all cases was at least 12 months worth of data, and in many cases over 2 years of data. So we actually had a pretty good time frame, many millions of rows of data that was kind of messy, and as you all know, it took most of our effort probably to wrangle that data. So just coming back to the uncertainty, I think it's important for us to understand and communicate, what does our study population represent? We cannot claim it's some, census level, statistically representative sample. It's essentially a kind of a Russian doll, and this is going to show us, just which version of the Russian doll it was that we were actually looking at. So if you consider all U.S. commercial buildings, a portion of those will have FDD. Then we have a portion of those that were provided to us in our data set. It was close to 1,500 buildings that we actually received data for. And then within those buildings, there's the whole spectrum of HVAC faults reported. We were only interested in the air handler, terminal unit, and rooftop unit faults within that spectrum. And so what we got was those faults reported by FDD that were air handler, terminal unit, and rooftop unit faults. And within what was reported, we couldn't really demonstrate this, but the truth is, even though it's messed up formatting, that for what we received, we could be fairly sure that there was a portion of those that were false alarms. That it's just a reality of things. We couldn't quantify that, but essentially we had that subset, and so there's going to be some uncertainty in the results, but relative to what we saw in past literature, what we had certainly seemed like a larger scale than anything that was reported before, and we think there's some good generalizations we can make with that. I mentioned how much data we had. We managed to trim it down to about, close to 18 million rows of data on faults. But we got a lot of data initially, that raw data. For example, when we looked at the actual naming of faults, in the raw data we received, there was over 2,000 unique fault names, which, there were just nuances in language. We spent a lot of time poring through that. We had the reported faults data for, as I mentioned, 1 or 2 years, the metadata on the equipment, and also some data on defining the faults themselves. We had a mapping step, so we could actually standardize on the fault naming conventions and also anonymize the metadata file so that anything we end up with cannot be traced back to any individual buildings or any individual building owner names, etc. And then the final piece of this, that the piece we actually could do the analysis on, was binary daily faults. So in this database, we had rows of data, and each row represented a unique fault happening on a piece of equipment in a building on a specific date. And we kind of built up from there. Now, even though FDD tools can report things that happen for 30 minutes or an hour, maybe there's a trigger threshold to say something's off, something's cycling, we really had to find a way to unify that to a higher level, which was daily for us. So daily means that a fault happened for some portion of that day. Could have been 24 hours, could have been 1 hour, but we had to standardize on something. So this fault day was our main unit of measure. And just for an example, a single piece of equipment might have several faults on a given day. So it can kind of add up to multiple fault days happening on the same equipment on the same date. And we ended up with almost 18 million. That was just for those three equipment types. So we had to filter out a lot of data to get to this. There were some faults that we didn't map because they were non-standard systems. Some we just couldn't interpret what the fault was. And some were fairly esoteric faults that we didn't think were going to show up too often anyway. So a quick word on the fault naming. A few people in presentations I've seen here have talked about standardized taxonomies for things like haystack for point naming conventions. There's this brick schemas, another alternative naming convention, but there isn't anything that gives you standardized HVAC fault naming conventions. That was something we had to actually develop here. Maybe it's something that it would be kind of nice if the industry could adopt a bit more standardization. That's for our selfish needs for doing research. But maybe for the industry too, there's some benefit in harmonizing how faults themselves are defined. But in our taxonomy, we got the 2,000 raw fault names down to around about 200 unique combinations of the fault ID, which included equipment type, where the system location was, if it was in the supply air region, the zone region, etc. We tagged it to specific components or parameters. I'll say more about that in a moment here. And then there were fault modes. So is the sensor biased? Is it frozen? Is a damper stuck? These kind of things for the fault modes. Now for the components or parameters, I think this is something which I think, again, in terms of communicating what FDD tools do and the fact that they don't always fully diagnose and point you to the exact cause of things, there are some cases where you can actually tag a fault to a component. Mixed air temperature sensor is demonstrated to be constant at a temperature of 200. I mean, that's definitely something wrong with that sensor that needs to be looked at. But in some cases, you might just be able to say, mixed air temperature is abnormal. We have an abnormal reading, and that could mean that mixed air temperature is truly out of spec in terms of its temperature, or it could mean that there's a sensor issue. It could be several causes, and you can't always nail it down just through data analytics with these automated tools. So here we have the components or parameters where certain faults could define a specific component, certain points just said certain parameters are out of whack. And in truth, when you're using one of these tools, there might be a lot of extra information that they're providing you to help you and give you clues to what the root cause is, or maybe a pick list of the top 5 possibilities. For the purpose of our study, we were just looking at discretely what was being reported. So the first question, as I mentioned, was thinking about what's the volume of faults that you actually will experience. And for those who are using FDD, I'm going to ask you if this jives with you. But if you take a particular use case, we all like to think, continuous optimization and continuous improvement. I think in practice we find a lot of organizations really continuous. Like, can you really sit at your terminal and say, I'm going to respond to this and this and this? In many cases it's just, we'll do a monthly review. Sure, if something really urgent gets reported, you've got to jump on it right away. But let's say if you're looking monthly at what your FDD had been telling you. What we saw is that you might find in a median building in our data set 245 unique faults reported across that month. And by that I mean if you have air handler 1 that has a chilled water valve leak reported, might happen every day, might happen 5 days, but that's just one fault that gets reported in that month. If the same fault is also on air handler 2, well, that's 2 faults for that month. So 245 as a median is kind of high. That's a lot of things to have to follow up on. And of course, there's a spectrum. We found sort of if you look at the whole population, sort of between the 25th and 75th quartile, you're going to get 27 to 274 faults. But really at the extremes, you know, if you're looking at a complex healthcare facility, you could be close to 1,000. On the other end of the spectrum, if you've got a few RTUs in a small retail facility, it might be a handful, 2 or 3, and hopefully you've got the operations team to support you in doing that. If you want to normalize that to individual units, for an air handler, we found that there's typically about 3 faults per air handler per month, and just over 1 fault per month for terminal units, which, I mean, that's going to really add up if you've got hundreds of terminal units in your building. So now here's the first piece here, just talking about the volume of faults. I'm curious for anybody who is using FDD right now. It's just like, well, yeah, that's exactly what we see. How do you deal with it? I see nodding here.
What's your experience?
We actually have a large base of service technicians. So as they get older, they can't find either anymore, but within my computer. But they have a better intuition of something you have to chase down.
Oh, really? Intuition on whether it's worth. Yeah, okay. Interesting. Anyone else have experiences they want to share on how they deal with the volume of faults they get in FDD?
We have a client that is using a fault detection diagnostics, and they're overwhelmed by the number of alarms. They are working towards, it's a slow process, they're working towards setting a hierarchy associated with the alarms or how valuable it is to address it immediately. They have a lot of buildings that they are monitoring across the university campus, and their aim is to fully automate the facility response calls through the FDD platform. But their goal before they implement that is 95% accuracy on the alarms as far as that hierarchy is concerned. And they're not there yet. And truth be told, from an outsider's perspective, 95% may be a high bar to reach.
Yeah, thank you. Yeah, so that for anyone who wasn't listening there or couldn't hear that, the point was about that kind of triage, that prioritization, getting to a point where you can really trust the faults to be something that really is a fault, that really needs to be addressed. And I would agree with the speaker there that 95% confidence that it's real and so forth is a pretty high bar. And but I think it does illustrate another key point that if you're taking on FDD, no one should expect that you implement it and great, good from day one. It's a long-term process. It can take you. I've heard people talk about 1 to 2 years even to feel like you're even confident in the data that's going into the tools, let alone what's coming out. And then for what's coming out, you need to really apply a certain level of judgment at the volume that you're seeing to be able to know what your action is. And to balance out the Nebraska comments, I'll mention something good about Iowa. So we worked with University of Iowa, who did some great work in this space, and they kind of talked about this two-level approach where they try and work out, okay, what do we need to react to straight away? What's the stuff that's going to either currently causing comfort complaints or is about to cause it or is a sign of imminent failure that they need to jump on? But then they kind of shuttle a certain amount of their faults into their next preventive maintenance schedule. So at that point, they actually have something that's, they've got a tool that's informing the processes they already have established, which seems to be working really well for them. Okay, so that's the volume of the faults. I'm going to dive a little bit more into the weeds here about the specific faults, what's most common. And I want to just maybe preface that by explaining the two dimensions with which we're looking at that data. So hypothetically, if this was our whole data set, we've got 4 air handlers, we've got 5 days worth of data. Of course, our data set is a lot bigger, but just to illustrate the point here, if we picked a specific fault, mixed air temperature abnormal, and we found that for air handler 1, it was fault-free for 4 days, then that fault occurred on the 5th day, so that air handler was faulted, or had the presence of the fault, or the symptom of the fault, on 20% of its time. And you can see for air handler 2, it's faulted 80% of the time, etc. So we can do that across all the equipment for all the different faults. So if our question is about how common a certain fault is, then we could see in this hypothetical data set that 75% of air handlers see this fault. That's kind of how common this fault is. And then if we want to say, well, you know, what portion of the time is faulted? How, I don't like using the word persistent because that maybe has some different connotations, but like how persistent, how commonly will this be reported to me? How common will this be a pain in the butt for me? And in this example, we can just take an average of those air handlers that saw this particular fault and say, on average, how often did they see it? In this case, they have a mean percent time faulted of 53%. These are the two metrics that I'll be presenting here on the next few slides here. We're going to start with air handlers. I'm not sure if I mentioned this earlier on, but with the time span that we've got here, I'm just going to talk about the air handler results and the terminal unit results. There'll be more to publish on this, so watch this space on rooftop units and additional insights. So if we look at what percent of the population of air handlers saw given faults, this is kind of a limited view. You know, we have so many faults, 50, 60 faults that we could rank on this scale, but just to make it visible on the slide, I've just picked everything that was 20% and above. Turns out to be 20 faults were showing up on 20% or more of the air handlers. At the bottom, we have the outdoor air damper showing up on average across all the different data sets we received. It shows up on 20% of the air handlers. At the top, outdoor air temperature, supply air temperature set point, outdoor air relative humidity. These are showing up on 50% or more of the equipment. That's pretty high. I will maybe mention one point here that what you see on this table here, there are variations between tools. So not every tool includes every one of these faults. Where they're displaying this, we're taking an average across all those data providers. So it's really, there's potential to skew, but really we're just looking generally at the relative scale of what's most common, what isn't. And these certainly seem like pretty high numbers. I mean, outdoor air relative humidity sensing, I know, is traditionally been a problematic area, so maybe I shouldn't be too surprised by that piece particularly. But supply air temperature set point, considering how important that is, I was surprised that was so high. So there's a lot here, so I'm going to pick out a few specific pieces of it. Maybe I'm not. This is an old version of the slides, by the way. So if I want to look at this, sensors show up. They're kind of more toward the bottom end, so return air relative humidity sensor, mixed air differential pressure sensor, flow sensor. I think we know that there can be problems with sensors, and they go out of whack. These are things that do get reported a lot. We see economizing challenges here. One of the things that is kind of interesting when you look at it at this scale is, as I mentioned a couple times now, that with the FDD tools, sometimes they can nail you down to a specific root cause or a specific component that is a root cause versus more generally saying, hey, a parameter's out of whack, you need to go find out what that root cause is. It tends to be that more at the top end, the examples where you don't get that full root cause diagnosis. So, for what you're going to see on these, you can expect the most common faults here to be the ones that are really going to need a bit of extra digging to actually find out what that cause is. One second. Okay. I'm flipping all over the place here. So I'm going to backtrack half a step here. So this was showing the percent that were affected, and this was showing the mean percent time faulted. So this is for those that see the faults, what is going to be happening over the longest period of time. So for this one, outdoor airflow. So for example, this is one where you may not see it on a lot of air handlers. It could be that not a lot of air handlers even have an airflow measurement station, but where they are in place, you maybe will expect them to have issues over a long period of time. Same with outdoor air relative humidity, supply air relative humidity, sort of shown up pretty high on the list here. Now if we look at both those dimensions, if we're going along the x-axis, that's becoming increasingly more common, occurring on more of the population of equipment. As we go vertically here, that's the faults that are occurring more persistently over a longer period of time. The upper right quadrant then is the faults that are common and persistent. These are the ones that maybe you would expect to cause you the most headaches and what you want to be most prepared to look at. And what you see here is, there's 7 faults picked out here in this upper quadrant. 4 of those are related to supply air temperature, either a problem with the set point, the supply air temperature measurement, the supply air static pressure set point. And I guess I'll just pause and just see if anyone here, if this jives with their own experiences. Is supply air the thing you would expect to have been most common and most persistent? Anyone have thoughts on that? Or anything else that's in that top quadrant? Outdoor air relative humidity? Yeah, in the back there.
I wouldn't expect it. I had a question. What is an error set point in terms of supply temperature set point?
That would be the supply air temperature set point.
Would that be like unusually high or unusually low?
I think that may be one of those where you're plugging into the sequences, and it may be related to a reset schedule where a certain set point is expected, but it's not actually happening. So maybe there's a conflict in the controls there, or some data issue that's causing a conflict there. I can't be more specific without seeing the list of all the raw faults that feed into that, but it kind of implies that you need to really look at the programming and set points to work out what is actually in conflict there.
It's supposed to be some set point, but it's not.
Sorry.
I was saying I can understand that in a common thing where it's supposed to bring that a set point, but there's a switch off in the programming and stuff.
Yeah, when you look at a lot of data, it's our platform, I can't really speak to that. I would say they're relative humidity too much, but I don't typically see supplier temperature sensors failing that much. But we see discharge air temperature, supplier temperature resets strategies fail constantly. Those are all the problems. We kind of understand we see those related to temperature reset sequences failing, we see those failing quite a bit too. So I see a lot of alignment with our upper rate or pile there.
Yeah.
What do you mean by this outdoor air relative humidity? And I think another list you had the outdoor air.
Yeah. That's a good question. I mean, when I saw the results, I had the same thought. So, obviously, you can't say, "Oh, the outside air temperature is wrong. It's faulty." But some of the tools will actually look at more logic-based rules, like we have an outdoor air temperature sensor. We also have a cross-check to a local weather station, or to another sensor in another building on the facility or campus or whatever. So it's looking at a mismatch that it cannot necessarily nail down to this sensor being wrong. It's just saying, hey, something doesn't look right here. It could be this sensor. It could be the sensor we're comparing against. It could be that the weather station's got some funky thing going on. But yeah, it's a good question.
I see how that makes sense. It's like a temperature sensor on a rooftop unit hood that gets like super hot, shows like 110 degrees when it's actually 90 degrees outside.
Exactly. Yeah.
Would manual overrides be captured, and how would they show up on this?
Manual overrides. Yeah, it's a good question. They would. I think they would show up in different places. Like there isn't. If we look at our list of discrete faults, we don't have one that is specifically called manual override. That could be one of the set point faults. Is saying that it's been constant for too long. If the software knows that the programming is that it should vary. So that's kind of hidden below the surface. That kind of issue. Yeah. Similar with scheduling faults that we don't necessarily say, you know, that it's the schedule that is reported. It's just saying, hey, look at this set point. Please somehow. Time here. How are we doing? Okay, so briefly on terminal units, there are fewer faults to occur, fewer faults being looked for in terminal units. So this is somewhat of a more compressed picture. So if we look at the percent of terminal units that observe a certain fault, again, here we have numbers over 50%. It's pretty high. You know, zone temperature sensor issues, you know, hovering around the 50% plus or minus, which that's kind of a lot. It seems like a lot, considering that HVAC is really about maintaining zone temperature. We don't necessarily see on this chart alone whether it's just an occasional issue or if it's fairly persistent. And I will mention at this point the whole 80-20 principle. Of course, you'll probably all be familiar with the fact that in some buildings you just get those terminal units that you can't quite get them right, can't quite get them balanced. In looking at both the air handlers and the terminal units, if we line them up and say which ones have the most faults reported versus the least, the top third account for 80% of all faults. So it's not quite an 80-20 rule, it's an 80-34% rule. And by an odd coincidence, it's the same for both terminal units and the air handlers. It's that rule kind of holds in both cases, that the top third of problematic units account for 80% of the faults. But you know, whatever. This on average, half of the terminal units to have these kind of issues is, I think, pretty high. It certainly speaks to a need for improvement. And if you think that the data that we've got, if you think about representativeness, my sense is that any building owner that wants to take on FDD and use it, that's probably an owner that's kind of got pretty good practices in place. They've probably got smart people on staff who are trusted to use this kind of tool. So if anything, this is, you know, going to be above the norm in the general population, in my opinion. Can't prove it, but that's my opinion. If we then go to the time dimension, you know, the amount of time spent faulted, we have 3 there that are pretty high. Zone, a couple of zone pieces, zone CO2 sensors, relative humidity, and also cooling. Cooling is so good we named it twice. This fault might be something like if the building's scheduled to be unoccupied with nothing running, but cool air is flowing, then we just call that a generic cooling fault, which can have many causes. So that's the cooling piece here. So, you know, half of the time or more to get these faults reported is definitely an issue. You know, that's going to play a big part in your life if you're using these kind of tools. Look at the quadrant here again in terms of what's happening most commonly. We again have 7 faults showing up in that top quadrant, which is more than 20% of units, more than 20% of the time. there isn't really a strong trend. For the air handlers, we saw that 4 out of the 7 were supply air related. In this case, we have a couple that are zone related, a couple to do with discharge air. I think that's just the general trend here. Maybe I'll ask again, what are people experiencing on the terminal unit side of things in terms of using these tools, or even without using these tools, what you see as the most problematic pieces there?
That zone temperature, it always baffles me that it feels like there's a gap or a disconnect between how many zones are so far out of whack in terms of space temperature versus set point. And then when you drill down with the operators and talk to the property managers, the complaints from the tenants don't quite match up with that. And I don't get it, but it's like sometimes you just think 5 degrees off for 4 hours in the day. Is that not a fire, you need to put out? And sometimes it's crazy how, nobody seems to care. I don't get it.
Maybe I wonder if people just get used to wearing a sweater to work if they're in the cold wing or what have you. It's coming to the back there as well?
It's something that we see to that point exactly, especially with new building commissioning, location of the temperature sensor and taking average space temperatures, one reading next to the window, one reading in the center, and then actually verifying that sensor, and then defining our suggested offsets for those sensors based on how the whole space actually feels versus just where that temp sensor is. The sensors don't tell the whole story. They just don't.
Yeah. Yeah, it's kind of scary, really, isn't it, when you think that, again, that's HVAC's whole role is to make the zones a certain temperature, and humidity and what have you, and it's a real, there's an art there to it. Yeah.
That very description is one of the challenges for operators to deal down on this. You just outline like a whole complicated, thermal type of discussion that an operator is not, want to dig into.
Wrapping that around. Yeah.
Another comment about that?
So you had an interesting graphic that showed a high percentage of faults for both zone temperature and for zone temperature sensor. So I was wondering, can those two pieces of information be taken together to infer that you're getting a lot of bad zone temperature readings because your zone temperature sensors have drifted out of the operation? And can that inference be made from the coincidence of those two things?
It's a good question. So to what extent can the zone temperature and zone temperature sensor faults sort of interplay and give us a bit of extra higher level information? From what I presented here, it's hard to see that correlation and how often are both things being reported together versus separately, and also other things that may also be reported at the same time. So I think in the individual case, it would be true that you can take these separate pieces of information together to get a higher level of insight into what's going on. From the generalized results that we have, I don't think we can really make that claim, but we can certainly do digging under the surface. It's a great question. Yeah, just go back.
This is a follow-up question to that, but I don't think there's any additional analysis to find a correlation between air handler faults and the terminal unit faults. I don't know if that's part of the presentation or not, but seeing airflow, for example, is really high in both cases. Is there sort of a correlation between something happening at the airflow or air handler and fix that as well?
Yeah. It's a great question. It's funny. I mean, I daydream about all these deeper level questions and going deeper and deeper and deeper, and we've got like almost 20 million rows of data and a million questions we want to ask of it, and but I'm always making a mental list of what I'm going to ask DOE for money for to do the next level, and that would be, I think, a really good question. Just trying to really connect an air handler to all of its terminal units and look at how those data relationships play out. All we've been able to do to date is really look at them somewhat in isolation. But we can, for instance, look at all the terminal units in a single building, but that doesn't necessarily tie the individual air handlers to their terminal units. And then you get kind of funky things like, how many terminal units might be running off the same sensor, and I'm not even going to go there. It's you all know it's complicated, right? And we're trying to get to some generalized conclusions here. Okay, better watch the time. So, just kind of in wrapping things up here, the things that we see as some critical needs coming out of this research, and not just that sort of the process for managing buildings, the process for implementing FDD, and also in terms of maybe building designers might want to look at these results and think about how they do their design work. So again, red meat to the sharks here. Commissioning is really good, right? And I really do want to emphasize this. I get cynical about marketing. I think these tools are great, but I think it's really important that the market understands that they are a tool to be used by an expert, whether that's your in-house team or an external commissioning provider or external partner. The tools don't do all the work for you. They do automated analysis, but they don't automatically optimize your buildings and automatically fully diagnose the root cause and automatically tell you what the solution is to fix it. So it's really important to keep hammering that point that these are great tools when used right by skilled people. There's a lot of things we could pick out, but I think that really getting a handle on the improved sensing to the degree that's truly sensing problems versus sensor location problems or the data communication issues and how they're handled. I think that, of course, the whole system is running based on what it's sensing is happening. So I think it's data, hopefully, from this research that emphasizes the need to really have a strong focus on that. Given the volume of faults, finding ways to prioritize systematically. If there are ways, some tools do this, there are different ways of doing it, but finding a way to actually prioritize. Can you rank the reported faults based on their impact on comfort and cost or potential maintenance impacts? These are ways that you can help get those thousands of faults to your top 10 that you can actually do something about in a short space of time. I think that's a really ripe area for more work. Improve root cause diagnostics to the extent that we can get more of these reported faults, honing in on exactly where you need to put your efforts. Again, that makes the most of finite resources that are there to fix the problems. And then this piece, if there are ways, we have some research going on at Berkeley Lab, which is looking at all the faults that might be reported by an FDD tool and thinking about if there's a subset that we can put in some logic that would automatically resolve those faults. That gets obviously very sensitive because there could be multiple causes to some of these faults. And if you take the case of an override, for example, it's all very well to say, oh, it's in manual, we should take it off a manual, but there was a reason someone did that in the first place, and you might want to think about that. But to the extent that some of the fault resolution can be automated, I think anything that can be done to reduce the volume of reported faults that you as an individual have to look at and do something about, I think that's certainly going to help. And moving on to my cool area, the research, things that we're interested to study some more. If we can expand to more equipment types, we already have data from the FDD tool providers on chillers and pumps. We just didn't have the capacity to analyze that. I'm sure there's plenty of insights we can draw from that. We could look at truly about persistence. In talking about the mean percent time faulted, we didn't really dig into this parameter of, okay, well, was it faulted for a month and then 11 months fault-free? Did it keep recurring? Did it occur for a month and then it came back 6 months later? I think there's something to be learned from there on a more long-term study that really looks at true faults and how they truly come back. And then the age-old thing of if we can just get more data. We did find between all the different data sets we received from different tool vendors, there are obviously going to be variations in the trigger sensitivity and how faults are configured. So there's variations in how many faults are being triggered of certain types based on how the rules are configured. certain owners might install things and then tweak the rules a little bit just to make sure they don't get too many faults along the way. So we're always looking for more data. If you have it, come see me. So that is the final slide. We have about 10 more minutes for any further questions.
Use up the questions.
Very quick, in terms of FDD tools, which ones were considered here?
Yeah, the question was about what FDD tools were included in this study. It's a good question. You know, we started out feeling very sensitive to what we were going to end up saying and how people might perceive what's being said and how they might connect that to specific tools. So we kind of started out with a blanket, well, we're going to keep that kind of secret. If there's anyone in this room who provided data for the study and wants to raise their hand and say, one of them's mine, that's okay. But we don't want to say too much. We were looking to get a large enough data set that we could just come up with these general rules, general insights without necessarily nailing down specific names.
But the faults are based on specific, how can I find it, tools, right? So they are not based on an analysis of anomalies. So it's more, for example, hey, my set point is supposed to be this, and that's my fault. It's not like we're analyzing anomalies overall, correct?
That is correct. Yeah. So the question was about how the faults were generated. In the case of all of these tools, as far as I'm aware, it's really about looking at the actual BAS set points versus actual measurements and saying something's off. Yeah.
Question about it?
So I was just wondering, I know you did studies over the last few years, first with the global pandemic and differences in occupancy. Did that impact all the studies, and so how?
That's a great question. Yeah, so the question was about whether the pandemic and COVID affected these results. In some cases, the data partners we worked with provided us data going well into 2020, but we cut our analysis off at the end of 2019 before all the shutdowns and things started happening. And again, just to the earlier point about all the questions we would love to ask, you know, where we've got data in 2020, we've often thought, okay, wouldn't it be nice at some point to look at what happened? And I suspect we'd be surprised at how many faults were still happening even when buildings were supposedly not even occupied.
And not supposed to be operating so much. It's a good question. Again, this question?
I was in a presentation just prior to this where a gentleman was from the New York.
NYSERDA, yeah, this guy right here, this one. It's a great presentation, by the way.
Different data sets that they have from what y'all are using, or you share, like, not. This SkySpark was an answer to his question for New York. SkySpark, Sky Foundry, was the winner as far as most implemented
Sites in the projects, yeah. Yeah. Yeah, it's a good question. You know, for anyone who did attend the NYSERDA presentation, Thomas Ye here did a great job talking about the work that they have done on a utility program style rollout. And yeah, many projects. We did talk at some point about if there was a way to use some of that data. It didn't work out, partly due to timing and the format of the data that we needed and the resolution of data we needed for this. But I think that there's, you know, more broadly, I saw a lot of complementary insights that Thomas brought in his presentation. So what the focus was for my presentation here was about, thank you, what the fault detection diagnostics tool is reporting to you, like that flood of data and those results, and combining that with the presentation from Thomas at NYSERDA, we get to see what is most commonly implemented. Those are the things that got to the point of full diagnosis, defining the fix, and going ahead to make that fix and the savings. So I think there's certainly some complementary insights there, and if we can finally get that data from you, Thomas, we'll see if we can add that in. Sure.
So I guess the obvious question is, we talked about the fact that faults don't necessarily result in what's the basis of the design and the system, which is to keep people happy with it. So the faults don't do that. We have all of these faults here. Is there any intelligence to this, to where you can say, let these things go, and let these faults go, and not make it, turn it into a service call, right?
Yeah, it's. So are you getting at what role the analytics can play in filtering out the things that don't need to be taken care of versus the ones that do? Of course, yeah, exactly. And I know going back a few years that there was conversations about wouldn't it be great if FDD tools can just issue work orders and really connect that system in a closed loop. And and you look at this, you're like, well, do you want like 300 service calls a month or 1,000 a day or what have you? Obviously, that's not reasonable. And I think that what you're asking there goes back to my earlier comment that it's really a long-term process that it ends up being quite site-specific. So over time, a certain site ends up learning a little bit more about what really turned out to be the important stuff that we needed to deal with. They might tweak their fault detection rules to account for that, so they don't get so many faults that really weren't worth following up on. And I guess I'm looking here at the more general level. There may be people in this room that have more specific answer to your question that's really at the site level. Like, what did we do to try and filter out the noise from what really needs to be taken care of? Go ahead, Thomas.
The interesting part about this is actually who is a fault correcting agent. And if the person that's responsible for this fault, for essentially take action from the FDDs, is actually the guy that had to fix it, you'd be amazed at how many of these alarms drops down. Okay, and that's one thing we notice is how careful the project is implemented during the commissioning of the fault detection diagnostic system. If the system, the guy that's provided installing the system is also has to be responding for fixing and presenting like which one should be fixed, like what is the priority, and then and a lot of these things actually goes away because that person used his knowledge of the building to filter out what the raw system output is.
Yeah. So I think the discussion has to be centered around to get the answer to this question is, there any kind of short-term research going on how to integrate or add modules of ML AI that will actually parse out some of these false alarms, or maybe even make the systems learn how to do that? And is there a movement towards that? I understand that we have a protection at this point, but what's the diagnostic part that we can kind of drive out of it is what the question I think is centered around it.
Like you have a fault and maybe a deadband problem, here's the solution to that.
And it could be just a rule-based sometimes to start with, if we can organize the knowledge base and then start firing, and then some sort of a fuzzy logic, which is not really in the literal sense. There is a AI-based rule, so that you can update those the weights and see if that led to a positive result, and then make the system learn and get those rules to fire first. That kind of thing. In a heuristic search method, some kind of use.
Mm-hmm. Yeah, and just to, I think, tell me if I'm paraphrasing this roughly right, you know, that you're just talking about the idea of using AI or machine learning to help create more of a loop that continuously informs that process so that over time the system builds into itself that intelligence about what was actually worth taking care of and what was the impact and feeding that back in so that in future that will bump up in the list or bump down on the list, I think is roughly about right. Yeah, I think that's a great point. I don't know of a lot of research that's really looking at that piece. So I'll make a mental note and ask DOE for some money on that too. With that, thank you very much.